Frankie Lai, we don't hear you.
Frankie, you're on mute, I believe.
Yes, I think also. Frankie, you are mute.
Can you unmute, Frankie?
Okay, can you hear me?
Yeah.
Thank you very
Yes,
much.
it's very good. Frankie, very good.
Thank you. Ladies and gentlemen, good morning and welcome to today's online lecture on fascinating topic, Abelian. Post-quantum privacy.
Hello.
Good
morning.
Yeah. Sorry that I may be let you out because you're so keep asking question. So I'm glad to be hosting this event on behalf of University of Surrey and the Surrey Academy for Blockchain and Metaverse Application. Our university and the Surrey Business School are committed to facilitating research, innovation, and collaboration in the field of blockchain and metaverse application. Our university, our Surrey Academy for Blockchain and Metaverse Application serves as a hub for cutting-edge research and development, bringing together academic, industry expert, and a student to explore the vast potential of these emerging technologies. Before we dive into subject matter, I would like to make a moment to introduce our guest speaker, Dr. Duncan Wong. Dr. Wong is the CEO of CryptoBlock, a blockchain company based in Hong Kong, with a strong focus on delivering cutting-edge distributed ledger technology solution. CryptoBlock has been as a fund of addressing enterprise changes in the blockchain space. I had a privilege of getting a note Dr. Wong through my involvement in blockchain student portfolio project that span across various universities in Hong Kong. In this opportunity, that I had a pleasure to connecting with Dr. Wong and learning from his expertise in the field. He's also a founding members of the project called Abelians, which aims to develop a quantum safe and privacy-serving cryptocurrency. So once again, I extend a warm welcome to all of you joining us today. And without further delay, I invite Dr. Wong to take this opportunity to take this virtual stage to share his talk about post-quantum privacy public blockchain project. Dr. Wong? Yeah.
Thanks, Frankie. Can you hear me?
Yeah, I can hear you very well.
Great. All right, so let me share my screen first. All right, can you see my screen? All right, thanks. Thanks, Frankie, and thanks to everybody coming over here. Thanks for having me. So I'm Duncan. So today, this is really a great privilege for me to come over here and share with everybody with this exciting project that I'm proudly being part of it. So this project is called Abelian, and I think in the coming 30 minutes, what I'm going to do is to share what we have done on this project, the purpose of this project, and also the roadmap about this Abelian project. So first of all, about the Abelian is basically, we call it a quantum safe, privacy preserving blockchain infrastructure. So what we are trying to do is to build a blockchain system, a public blockchain system, which is quantum safe. I'm going to explain what we mean by quantum safe. And also another part of the set of features is privacy preserving. We basically believes that in the next generation of blockchain, we need to be quantum safe as the first criteria. And the second part is that it would be nice if we also have privacy preserving for everybody. So let me just dive in to the background and also to explain about why we would like to do this kind of projects. So first of all, about a little bit background regarding the quantum computing is that basically in recent years, not decades, the quantum computer development has been advanced quite significantly. So if we look into the timeline over here, 4 years ago, Google and IBM, they independently built the 53 qubit quantum computers. So this is kind of like a toy for quantum mechanics scientists, but this is basically a breakthrough because they basically demonstrate that we can basically play around with those qubits and try to implement some of those quantum algorithms using these real quantum computers. And then in the past 4 years, we've been seeing a lot of development on the quantum computer. And very recently, IBM built 1000 qubit general purpose, or we call it the universal quantum computer. And also there is a pretty promising advancement in the coming few years that IBM predicts that they will be able to build a more than 4000 qubit machine in 2 years' time. And also they jointly work with some other universities and research centers that they are planning to be able to achieve a quantum computer which can achieve more than 100,000 qubits in 10 years' time. So there are also some other startups joining into this industry, and some of them even claim that they will be able to build a 1 million qubit in the very near future and raise a lot of money for building these kind of machines. So why do we need to talk about the quantum computer? The main reason is that the quantum computer, once it becomes mature, it basically poses a great threat to the existing public blockchain technologies, for example, Bitcoin, Ethereum, or basically all existing conventional blockchain systems. So the next question that we would like to ask ourselves is that how would this quantum computer be a threat to the existing blockchain systems? So if you look into the Bitcoin system, basically the Bitcoin system is basically replicated to many other blockchain systems. So this diagram basically shows how the Bitcoin or basically the wallet keys are being generated. So to start with, we start with this private key. And based on this private key, we will be able to generate the public key. And then from this public key, it's basically hashed into the public key hash, and it's further encoded into the address that we know or we are familiar with. So if you look into the algorithms over there, there are two basic classes of algorithms being involved. The first one is the elliptic curve digital signature algorithm, the elliptic curve DSA. Another one is basically a bunch of hash functions, for example, the SHA-256 or the RIPEM 160. So about these algorithms, if you are a little bit familiar with the quantum computer, we know that there is a very famous scientist called Shor. And back to almost 30 years ago, Shor has this algorithm, a quantum algorithm, which basically demonstrates how to break discrete log problem. And later, this algorithm can be further derived to solve the factorization problem. So what that means is that the algorithm can further be extended to break elliptic curve private key from its public key. So which implies that for Bitcoin system, once this private key is, once this public key is given, then by applying the Shor's algorithm, then the attacker will be able to derive the private key. So we are not talking about like deriving from the address back to the private key. We're talking about deriving the private key from the public key rather than the address. Because if you want to derive directly from the address back to the private key, we actually need to reverse this hash function. And Shor's algorithm does not apply to this hash function. So in order to break Bitcoin by using Shor's algorithm, we actually need the public key of that particular wallet. So the follow-up question is basically like, where can we find this public key? And where does this public key stored? And actually, if we look into the Bitcoin white paper, the most famous Satoshi paper back to 2009, and also if you look into the GitHub, the source code of Bitcoin, what we can realize is that the public key is actually on the chain. So if you look into this diagram, for example, if we look into this, the middle column, transaction from B to C. So if, for example, if we want to compromise B's private key, the first thing is that on the blockchain, you will be able to find B's public key. And also in some of the previous blocks, you will also be able to find B's address. So basically from this public key, we can hash it and to check whether it is the same as B's address. And also from this public key, we can apply Shor's algorithm to derive Bob's or B's private key. So that's why basically if the attacker is we call it the eavesdropper, and this eavesdropper just download the entire block ledger from the Bitcoin system, then this attacker will be able to just handpick a particular wallet and try to crack it by recovering or compromising the private key from the public key. So there are some research work being done on the estimation of the time in order to crack it. So some of the papers, I just quote one of the recent ones, estimate a quantum computer with 317 million qubits will be able to break Bitcoin system in about an hour. So by breaking the Bitcoin system, as you can see, it basically means that you can basically compromise all the wallet addresses of Bitcoin. As long as the wallet address is being used to send some of the Bitcoins out, then that wallet will be able to compromise by a quantum computer. So in fact, if we look into some recent development of the post-quantum cryptography, post-quantum cryptography basically means that we look into how to build encryption and digital signature algorithms which are secure against quantum computers. Or basically what we mean is that it's basically need to be secure against Shor's algorithm and also some other algorithms like Grover's algorithm and some other related variants of those algorithms. So there is a very good presentation that recently done or provided by the NIST, the National Institute of Science and Standards and Technology of the USA. And in this presentation, there was one slide that I coded over here. It basically gives a kind of like an overview about what kind of algorithms would be vulnerable to the quantum computer. So if you look into the crypto standards, the tree over here, on the left-hand side, it specifies the public key encryption algorithms or digital signature algorithms. For example, the FIPS 186, or the key establishment, the 856 A, B, or C. These algorithms in the algorithms that we are currently using, for example, the RSA or DSA or the Elliptic curve DSA, they are all vulnerable to Shor's algorithm. So in terms of the encryption, for example, the RSA encryption or some of the exchange protocols, for example, the Diffie-Hellman or the elliptic curve variant of the Diffie-Hellman protocols, they are all vulnerable to attacks from quantum computers. So how about those symmetric key encryptions? For example, the AES that we are currently using, or those hash functions, for example, like SHA-1, 2, or 3. So should we continue? All right, okay, so let me continue over here. So about those symmetric key-based encryption algorithms or hash functions, they are basically still secure. Because if you look into some of those literature, for example, Grover's algorithm, the Grover's algorithm will be able to reduce the complexity of attacking by half, but that's not significant enough to break those algorithms. So for example, if we want to achieve 128-bit security by using AES, all we need to do is to increase the key size from 128-bit to 258 bits, 56 bits, 256 bits. So basically, if we double the key size or the output range size of those hash functions, we will be able to secure against the quantum computers. So symmetric key-based are fine, are just fine. But the public key-based is the key issue over here.
Excuse
and that's why
me. I have a question. Because why is it SP 870A? So I don't know why it's the key-based.
So
probably I don't know.
I'm not sure whether we would finish the presentation first and then they answer the questions. Or...
Natural. Okay. Okay.
Sure. Thanks. Yeah. So
thanks.
That's a good
Also,
question. Thanks.
Thank
Thanks for the question.
Good
so maybe I just finish the presentation
and it's okay.
And then we will address that during the Q&A session.
Okay. Thank you.
All right. Thanks. So let me continue over here. And so basically, according to the Shor's algorithm, we will be able to break the existing elliptic curve or the basically anything which relies on the discrete law problem or the factorization problem. So in the next slide, what I'm going to talk about is basically the effort that the researchers have been doing in the last 1 to 2 decades, that we are trying to build some post-quantum systems which are secure against quantum computers. So if you look into the US NIST standards, back to 2022, some standardized algorithms has been selected. So for example, the KEM, key encapsulation mechanism, basically you may consider that as an encryption algorithm. The crystal Kuiper has been selected by the US NIST as basically the algorithm to be standardized. And about the signatures, there are 3 algorithms being selected to be standardized by basically next year. Crystal Lithium, Falcon, as well as the, I don't know how to pronounce it basically for this one, but this is the hash-based one, spinach or or something. So basically that's the 4 algorithms have been selected to standardize. So if you look into the post-quantum cryptographic systems, there are 4 major types: hash-based, code-based, lattice-based, and multivariate quadratic equation-based. So among these 4 approaches, the lattice-based is one of the most popular ones. So in fact, last year, NIST published 4 schemes, and 2 of them were selected as the primary algorithms for general purpose applications, which basically means that if you want to encrypt your system using post-quantum algorithms, if you want to sign your message using a post-quantum algorithms, these 2 algorithms are basically like recommended ones. So you may pick them and it will not go wrong, basically. It's called general purpose applications because they are fast enough for general purpose, they are small enough for the general purpose, and also secure enough. So both algorithms are lattice-based, and they are used in our system, Abelian. So speaking of the Abelian system, as I have already mentioned quite a bit, Abelian is a post-quantum blockchain, which basically means that we are making use of the post-quantum digital signature and also a little bit of the encryption algorithm in order to achieve the security of the blockchain system. So it's different from Bitcoin, Ethereum, or other major conventional algorithms that they are all based on elliptic curve cryptography. So Abelian is based on lattice-based cryptography. So in addition to the lattice-based cryptography, Abelian is also supporting multiple levels of privacy preserving features. So over here, there are basically 3 privacy levels that Abelian is supporting. So the first one I would like to introduce over here is called full privacy. So full privacy basically means that the sender's wallet address is hidden. The receiver's wallet address is also hidden. Hidden means when somebody look into the blockchain ledger, they will not be able to find out exactly what the wallet address of the sender is, what the wallet address of the receiver is. And then the third part is called amount hiding, which basically means that the transaction amount is also encrypted. So if you think about some similar systems, Monero and Zero Cash are basically in this category. They all support full privacy. So the main difference between Monero and Abelian is that for Abelian, it makes use of this lattice-based cryptography to achieve full privacy, while Monero is using elliptic curve cryptography for achieving the full privacy, so which is not quantum safe. So this is the first level, and which is basically the highest level. The second level, we call it the pseudonymity. And pseudonymity is basically very similar to Bitcoin or Ethereum. I call it anonymous but traceable, which means the wallet addresses are basically like randomly generated. There's no information regarding who's behind a particular wallet address. So there's no KYC, it's purely anonymous. That if you are using MetaMask or some other kinds of, say, Ledger Nano or some other kinds of wallets, you know that it's just a random looking number. And whenever you send the information out, your identity will not be leaked. However, all your transactions are traceable. So that's why, for example, if you go to Etherscan, you will be able to find out all the details of the transactions. You can follow, you can trace all the transactions. You will be able to find the balance of every single wallet because it's traceable. So this kind of anonymity level, we call it the pseudonymity. So for Abelian, we support actually full privacy as well as pseudonymity. It's actually up to the user to choose which level that the user's wallet would like to be. And I also believe that this is kind of like the first blockchain system which can support this kind of multi-level privacy enhancing technology. And there is one more level of privacy, which is called accountability. So accountability is something in between full privacy and pseudonymity, which basically means that for the public or eavesdroppers, the accountable wallet is still untraceable and anonymous. So it provides full privacy. But in addition to that, there is also a tracking tag. So you may consider there is some additional information that the user can share this tracking tag with a third party. And this third party will be able to so-called downgrade the privacy level from full privacy to pseudonymity. So for this third party, the third party will be able to trace all the transactions coming in or going out of that particular wallet. But this third party will still not be able to find out who's really behind that wallet. So it basically provides the pseudonymity level of privacy to the user against this third party. So these three privacy levels that we are providing is mainly for like different kinds of applications. For example, if you're if you are using the Abelian on the dark web, I'm not encouraging any of the criminal act over here, but this is basically the freedom of use of this Abelian system, that you can basically make use of this full privacy feature of Abelian to send transactions. For example, if you are, say, residing in some kinds of jurisdiction that full privacy is forbidden, and you have to use a pseudonymous wallet, then you can still use Abelian by using those wallets which are pseudonymous. Or in some of the jurisdiction that full privacy is allowed, but maybe there is some kinds of authority that the authority may have access to some of the tracking tech, so that for the authorities, the security level or the privacy level is on the pseudonymity, but for the public, your privacy level can be fully private. So we are providing all these features, and we basically welcome the industry or the community to discuss about that and to propose what kind of applications that we would like to use for different kinds of privacy levels. So in the coming few slides, I'm going to give a very high level technical overview about how we achieve full privacy. So over here, I'm just taking an example from the Monero. As you can see, the symbol is XMR, which is Monero. And Monero has a very good illustration about how the linkable ring signature or the ring signature works, and how this is used for protecting the sender's anonymity. So as you can see on the left-hand side, for the ordinary signature, for example, like Alice would like to generate a signature. Alice basically uses her private key to generate a signature. And then everybody can make use of Alice's public key to verify the signature against the signature, against the message. So everybody has to know who's the signer. But for ring signature is quite different. For the ring signature, the signer is one of a group of potential signers. So in this illustration, we have Alice, Bob, Carol, and any one of them could be a potential signer. So for example, like Alice generate the signature, but Alice pull in Bob and Carol's public keys together with Alice's public key, and Alice makes use of her private key to generate this ring signature. In order to verify this signature, we actually need the public keys of all Alice, Bob, and Carol. So you can still do the verification of the ring signature and can verify that one of Alice, Bob, or Carol has signed the message, but you will not be able to tell exactly who's the real signer. So this is the ring signature's additional feature when compared with an ordinary signature. So about the linkable ring signature, it's just one thing built on top of this ring signature. Namely, if the same signer generate two signatures for the same message, then the verifier will be able to find out the identity of the signer. So this is different from the ring signature, because for the ring signature, if the same signer generate multiple signatures on the same message, then the verifier will not be able to tell who's the real signer. So the linkable ring signature is basically used over here mainly for preventing double spending on the blockchain setting. So this is one of the building blocks, and the linkable ring signature was co-invented by myself back to 2004. That's almost 20 years ago. At that time, we had no idea actually linkable ring signature would be able to be used on the blockchain for such a great feature. So this diagram is a little bit complicated, but this one basically illustrates how the Abelian works, how the Abelian make use of linkable ring signature and zero knowledge proof, as well as commitment scheme to build such a privacy preserving blockchain. So let me just quickly go through it. And after the talk, I will be more than happy to share this PowerPoint with everybody. So over here, what we are trying to do is that starting from the left-hand side, the con address basically is your actual wallet address. And the real value over here is about the number of ables you want to transmit or you want to transfer. So first of all, we use a commitment scheme to hide the real value of the transaction. So you may consider a commitment scheme as an encryption scheme, but it's one way. So it basically protects the real value. And when you send this commitment scheme onto the ledger, onto the blockchain, nobody will be able to recover the real value except the receiver. And then we make use of the ring signature to hide the real coin address among all the other fake addresses. And in addition to that, we derive a one-time coin address from the real coin address. So every time when we look into the ledger of Abelian, you will not be able to find the real coin address. Every time is a brand new one-time coin address. So this is kind of like double layer protection, that in addition to using the commitment scheme to protect the real value of the transferred amount of this transaction, we also use one-time coin address to protect the sender's wallet address. So now you can see that on the ledger, there will be a bunch of one-time coin addresses. Actually, we have 7 coin addresses in our real implementation. And also we have 7 commitment values. In addition to that, we also add in a zero knowledge proof. This zero knowledge proof is used by the receiver to verify that, or basically by the miners to verify that there is no double spending. So we verify, as you can see in the description over here, the zero knowledge proof is to show that the commitment scheme over here contains a value, which is basically the output value is the same as the input value, to make sure that there's no double spending. So if you would like to learn more about the details of the algorithms that we proposed and we composed, and also we implemented, you may check out our white paper available online. So in addition to that, recently I also published a yellow paper. And on this yellow paper, what I have written up is basically an idea about how to make use of Abelian to upgrade other conventional systems so that other blockchain systems will also become post-quantum. So for example, you have, say, Ethereum system, and we basically propose how to make use of this post-quantum zero-knowledge bridge technology to upgrade Ethereum system to post-quantum by using Abelian as kind of like a layer 0. So for more details about this, I think I'm going to skip over here just to make sure that it's not too technical to bore you guys. But basically, what we are doing in this yellow paper is that we basically create 2 post-quantum zero-knowledge proofs. And in these 2 zero-knowledge proofs, what we are showing is that the one who generates the public key pair on the Abelian system is also the one who generates the wallet on the conventional system. So in this diagram, consider blockchain B is Abelian and blockchain A is, for example, say Ethereum. And what we are showing by using this zero knowledge proof is that the user who generates this public key, post-quantum public key, as well as the corresponding private key, is also the one who generates the wallet address as well as the public key on the Ethereum system. So we make use of this zero knowledge proof to link these 2 addresses together. All right. So the next thing I would like to describe about is basically the Abelian halving. So first of all, the Abelian right now is still proof of work as a POW. So every 3.25 years, there will be a halving happened. And the circulation basically is mandated in the following ways. So the total supply of Abelian is about, is a little bit more than 200 million AVOs. And every 256 seconds, there will be a new block coming out, generated or created by a miner. And right now we are still at the first era. And for each block, the award is 256 AVOs. There are altogether 10 eras. So this is how we generate all the supplies. And in addition to that, there is a less than 10% pre-mined 20.58 million AVOs being pre-mined back to last year. So to date, we've been mining for a little bit more than a year. Everything's going very well. And in the very near future, we are also going to upgrade the system a little bit in order to make it more efficient. So at this moment, the throughput is about 8 transactions per second only, so which basically sucks in terms of the scalability. What we are currently building, and probably in 2 to 3 months' time, is to have a little hard fork for the Abelian that we can boost the transaction per second to 64 transactions per second. And later on, we also have a plan to upgrade this POW to POS, and also to build the layer 2 by making use of the post-quantum zero knowledge bridge to connect the Abelian with the layer 2. And we try to achieve 1,000 transactions per second for layer 2. So finally, what I would also like to encourage everybody, if you are interested in Abelian, to start contributing to Abelian by doing the mining. So while you are doing the mining, you will also be able to earn the Abelian tokens. So you can do the CPU mining as well as the GPU mining, despite more and more folks are doing the GPU mining, because if you look into the mining speed, the CPU just cannot compare against the GPU mining. So for the GPU mining, one single GPU card will be able to achieve 40 to 50 mega hashes per second, while for the CPU, we are only talking about a few hundred kilo hashes per second. So basically one GPU is about like 200 to 300 CPU cards, CPU or machines in terms of the hashing speed. So if you are interested, if you have any spare gaming machines, or if you have any spare laptops that you would like to join the Able mining, please feel free to do so. The link is over here. Actually, if you mine, you are actually also helping Abelian to be more decentralized and also to be more secure and robust. So finally, this is basically my Twitter handle. So please feel free to follow me. And also from time to time, I'm also sharing my insights and also the development about Abelian. So if you would like to learn more about Abelian, please go to this Linktree link. You can find all the links related to Abelian, or just go to abelian.info, which is our website. And if you are a researcher and you would like to find out all the details of all the algorithms that I mentioned, for example, the post-quantum linkable ring signature, and also how we built our stealth address, please feel free to download those papers and go through it. We are also going to have another new paper coming up, which is about how to make Abelian even more efficient, that I mentioned about the 64 transactions per second. So that's what is coming up in the coming few months as well. Thank you all for listening to this presentation. I hope that you find this interesting. And I think the second part is about the Q&A part. So maybe let me just address the question that's being raised just now. So regarding the post-quantum part, or basically about the quantum computer, what we are trying to do by using the lattice-based is that we try to make sure that those quantum computers would not be able to handle the error or the noise being introduced. Basically, the lattice-based cryptography is about introducing noise into the system, and the private key is kind of like an error correcting code. So the private key will be able to correct the noise and being able to decrypt the message or to verify the signature. But without the private key, the noise is just so big that the quantum computer will not be able to figure out or to rectify those noise. I believe if you have learned something about the quantum mechanics, you will know that the most challenging part about building a quantum computer is about eliminating the noise when constructing those qubits. So basically by using the lattice-based cryptography, what we are trying to do is to magnify the noise and make the Shor's algorithm not being able to perform efficiently, or any kinds of quantum algorithms being able to perform efficiently. And also the question about those US NIST standards, for example, the ECDSA or the RSA, they meant to be replaced by the post-quantum algorithms, and the standard will be published by next year. But basically, you can actually go to NIST website now by searching the NIST post-quantum cryptography, and you will be able to find all the details about the algorithms that they are going to standardize next year. And also right now, the federal government and also some major companies, they are already preparing for the migration from elliptic curve cryptography into post-quantum cryptography. All right, thanks. So let me just go through so Frankie, should we just go through some of the questions over there?
Yes, please. Duncan, do I need to send you the question through the chat?
I'm just going through the chat over here. For example, Amit is asking any mining benchmark comparison on a single GPU.
Yeah.
I have some, but I don't have one for the list over here given by Amit. For example, like we have tried on the NVIDIA GTX 3060, 3070, 3060 Ti, and all that. And the speed is about 40 megahashes per second to 50 megahashes per second. So that's about it. But if you would like to get more information, because we are basically making use of the e-tash. So let me just type it on the chat over here. Because we are basically using the e-tash for Abelian, so you can actually search for the benchmark, hash benchmark of the e-tash, and you will be able to find more information online.
So hi Duncan. Thanks for your presentation and detailing the and giving a high overview of the algorithms. Yeah, so it will be a similar benchmark to e-tash as well, like for GPUs, like if we do mining for Abelian.
Yeah, so in terms of the benchmark, it's going to be very similar in terms of the mega hashes per second. That's right. And another related question, Amit, is that how many Abels that you will be able to mine based on your current speed. You may go to I think it's called explorer.abelian.info. So I'm just typing.
I see. Thank you.
Yeah, so you may actually go to Explorer and check out the difficulty level over there and compare the difficulty level with your hash rate.
Yeah.
And then you will be able to find out like the proportion of your hash rate versus the entire difficulty level of the network. All right.
Yeah.
So there's another question over here. Yeah, thanks, Amit. So another question is that, can you please clarify, does the accountability model provide the same privacy as Monero, except that there is a designated party, such as the party sees such transactions as if they were in the pseudonymous model? Good question. So about the accountability model, let me just go back to the accountability or the multi-level privacy slide. Okay. So about the accountability level to the public, you are right. So to the public, we achieve the anonymity at the privacy level as of Monero or Zcash. So to the public, the sender receiver, their addresses are all hiding. So basically we use the one-time con addresses. And also the amount is also hidden by using the commitment scheme. So for the accountability model, because there is a tracking tag And that tracking tag is a little piece of information that once the authority or the third party has that tracking tag, then basically that tracking tag will be able to link a one-time address with the real world address. And that's why the third party will be able to find out the real world address and then trace the transactions corresponding to that real world address. So getting back to your question over here, to the public, yes, we provide the same full privacy level as of Monero and Zero Cash. To the third party, we provide the pseudonymous level to the third party.
Thank you, Duncan. That was my
right.
question. I just had a quick follow-up, if I might, about any applicability to CBDCs that you see, or other places where regulation and blockchain kind of come together. It looks like somebody else is. Thanks.
Yeah, thanks for the question. Short answer is that I don't quite know, but actually in the past few years, I've also been working on the CBDC. In Hong Kong, I've been helping Hong Kong Monetary Authority and also Bank of Thailand to build some prototypes of the CBDC. Based on my experience, what they are focusing on is actually really not about the privacy we are talking about over here, to be honest. So what they are talking about, the privacy, is really just the privacy to maybe to the public. For them, they have the entire audit trail. So you may basically imagine that this accountability thing, the tracking tag, is kind of quote unquote inspired by them. But the main purpose of having this tracking tag is really for some corporates that they would like to, for example, set up a virtual payment systems within their enterprise or their corporate, and then they would like to make use of this tracking tag to track for that particular wallet. But definitely, I think the Abelian technologies over here might be useful to some of the CBDC building blocks or some of those projects. I'm not so sure. At this moment, what I learned, for example, the mainland China CBDC, they have this ECNY, which is not based on blockchain. And they have that 2 tiers. The first tier, that between the central bank and those banks, they are basically having kind of like a audit system with all the detailed information, with all the detailed information being shared with the central bank. And then for each individual bank, they will be able to issue this ECNY to retail customers or to those merchants. And for them, then the anonymity is not there to the bank itself. So the bank will be able to find out all the information. But for those retail customers among them, there is a certain level of privacy protection by segregating their transactions and not being able to let them access all the information because it's basically not a public ledger. Yeah, so I'm not sure whether I answered your question or not, but these are some of the experience that I share.
No, very useful. I think nobody knows anything for sure at this point. Thanks.
Thanks, Chris. Yeah, so there's also another question from Abelian. Yeah, I'm also a big fan of the Mendel stuff. So any chance to shorten the wallet address? Yeah, that's a good question. In fact, in the coming few days, I'm still doing the final testing, but in the coming few days, we are going to publish a new desktop wallet. The new desktop wallet is going to support the short address. So for those who are already using Abelian, you guys must be suffering from the long address, which is just super long, 20K character long. And it's very hard for you to copy and paste or transfer to another machine and so on. So currently, we have built a short wallet address, which is only 64 bytes long. Yeah, hooray. finally we have a smaller one, and yeah, we are going to launch it out real soon in the coming few days. So the desktop wallet will support that first, and then later on we are going to support the CRI as well. Yeah, looking forward to that. Yeah. Any other questions?
Yeah, Duncan. So I have one question. So so it's related to scalability. So in layer 2 we do have this lightning network, and I think this was so there was like you might be aware of the wormhole attack, right? So so my question is basically how if this post-quantum blockchain or the technology, let's say if we to actually have this technology cater to the scalability of the for the off chance layer 2. So if we wanted to have like this, so there's like a, I think, adapter signature it is called, if I'm not wrong. So it's called like, I think, scriptless script, something like this. So there's a different way where you can actually reveal the secrets of the given signature. I think in post-quantum it is termed, I think, adapter signature. Sometimes is also I think it's similar to scriptless script as well. So my point is like because I think this wormhole attack was actually mainly due to the signature issue, and I think it was something similar to scriptless script mechanism. So my point is, what if we adapting some layer 2 strategy like payment channel network, or maybe state channels for this scalability, and we also have this signature like similar capability of the digital signature with this adapter signature via the post-quantum cryptography. So how do you think that because the idea is actually to resemble the lightning network, so how do you think like or what are the scopes of some layer 2 strategy that we can make use for scalability and also improving the sort of security aspect?
Sure. Yeah. So basically, when we are talking about the blockchain trilemma, right? When we talk about the blockchain trilemma, scalability, security, as well as decentralization, for Abelian, basically we are just focusing on 2 of the 3 in the trilemma right now. The scalability is not the part that Abelian is currently addressing. So we are only addressing the security as well as the decentralization. On the scalability part, my view about the design of Abelian is that we probably have to address that at the layer 2. The reason is that we have this technological challenge or barrier that we are facing, is that when we are using this lattice-based cryptography, one major trade-off is that the size of the signatures are just too big. So for example, when we are using this linkable ring signature, post-quantum linkable ring signature, each signature is 4 kilobyte. So that's the size of a linkable ring signature, versus say on Monero, one linkable ring signature is about 200 byte only. So if you just think about that 200 bytes versus 4 kilobyte, there's no way for us to really have a very efficient way to improve the scalability. And definitely this is an open question that we welcome other researchers to come up with a more efficient way to build this Abelian in the future. But this is basically the current challenge, is that the signature sizes are huge. The zero knowledge proof, the commitment, the lattice-based commitment, they are all huge. So in fact, some of the current miners, they have been like recently they have been like transferring abled from one water to another, they actually experience that the block size actually reaches 8 megabyte easily. Like after crunching in 18 transactions, the block size is already 8 megabyte. So there would also be some problems regarding the propagation of those blocks if the block size is too big. So that's why what we are trying to do is to make Abelian, so-called this layer 1, as simple as possible. It's just one single purpose, which is to do the fund transfer. That's it. There is no smart contract support. There is only a very little scripting language being supported. And that's why we have this yellow paper coming out, this lattice-based bridging technology. So this one. And then we will build the layer 2 and making use of this layer 2 to build the post-quantum smart contract ledger. So to answer your question, what we are doing right now as a framework is that layer 1 Abelian will remain as is, which only focus on the security as well as decentralization. And then in terms of the scalability, the reason why we want scalability is that we need to support as many applications as possible. Then we make use of this layer 2 to support that. And for the layer 2, we make use of this bridge. And also we will be able to make use of POS rather than POW in order to further increase the performance. We will also make use of some other ideas that we will be able to borrow from other traditional systems like Ethereum, Solana, or Cardano by using, say, for example, the sharding mechanism and some other kinds of segregation mechanism. Even recently, we have also been looking into algorithm system to see whether there is any good ideas that we can borrow over for our layer 2. Yeah.
Thanks for answering and clarifying the scalability aspect. So I think also I think you're making use of zero knowledge proof in the transfer of the transaction, right? As well. I think if I'm not wrong, I think slide you. So my other question is, so do you also support atomic swaps, like exchanging different cryptocurrencies? Because okay.
No, not yet. So at this moment, we may not be able to support atomic swap. What you mean is to have two different currencies to be able to exchange with each other, right?
Basically sort of trading, because in DeFi you only is like
sure. So the atomic swap or any kinds of other smart contract based applications will be done on layer 2. So that's what we are going to build on the layer 2. But for the Abelian layer 1, we will not be able to support other cryptocurrency. There will only be one native token which is able. Yeah, that's a good question. Yeah.
Thank you, Duncan.
Thanks.
Is there any question?
Yeah, so it's UTXO based. Sure.
I think that's the end of this Q&A session. No more question from my side.
All right, thanks.
So Duncan,
thanks for joining this.
So maybe actually I work with the same team as Frankie, and of course we will I will have maybe further question later. So I will have a look at your white paper, because I think you already shared the link. So I'll have a detailed look over it, and if I will have any further question, I will ask Frankie your email to to reach you out.
Sure. Sounds good. Yeah. So for everybody here, if you would like to reach out to me, feel free to search my name, basically like Duncan Wong Abelian. You will be able to find my contact over there. Thanks for joining this. And Frankie, if you would be able to share the PDF to everybody over here, that would be great.
Yeah, sure. I will share the PDF that you share to me to anyone join this session. And thank you for all participate today. And thanks for Duncan give so insightful, informative session. And we hope that we can continue our collaboration, and we may ask for your help in the future.
Thank you.
Thank you.
Sure.
Yeah,
right.
UN like
See you
this
guys.
today. Yeah, will be continued from our side, our Survey Academy for Blockchain and Metaverse Application. Thanks for your join today, and see you soon. Bye-bye.
Thank you.